Hello. Today we're going to start talking about the connection between trigonometry and the Pythagorean theorem. The whole trig unit deals with right triangles, and so there is a deep connection between the Pythagorean theorem and trigonometry. And we'll just highlight one particular connection. So our objectives today, our students will be able to use trigonometry with pyramids and label the appropriate lengths. The other objective is students will be able to define the Pythagorean theorem. Vocabulary that you might hear is slant height, pyramid height, base, apex, Pythagorean identity. So within that first example, we're going to work with a pyramid. What is the common right triangle was probably modeled in the construction of the triangle in figure 2. Okay, and we have to kind of use figure 1 to get to figure 2. But before we get to that, I want to label this. Right here, the top of the pyramid, we call this the apex. Okay, so as you're looking at these things, just the very tippy top of that pyramid, that's what we are going to call the apex. Okay, the pyramid height is the apex down to the base. So that perpendicular right there in pink, that is what we call the pyramid height. The next important piece of information is the slant height. Okay, and so the slant height goes along the face of the pyramid, and so this is the slant height. Highlight that in blue for you. And finally, what we have is the base. So the base is this whole entire distance. And if it's a square pyramid, which this one actually is, it's the other side also. Now, the question itself says, what common right triangle is probably modeled in the construction of the triangle in figure 2? We don't have figure 2 because we had to create it. And what figure 2 really is that embedded triangle. So I'm doing my best to draw it out accurately. And so let's go back and label. This is your pyramid height. This happens to be your slant height. This is 53 degrees as described by the image. And the last bit, you'd be like, well, why don't we highlight the bottom part in yellow? Because the base is actually only 1/2. Okay, the way the pyramid in this square pyramid is, it's really only the 1/2 of this yellow part. So we can highlight this in orange, but the base is only 1/2. And the reason why it works that way is because this is parallel. This triangle is parallel to that. All right. And so it asks us to kind of look at this. It says the sine of 53 degrees is equal to 8/10. And fraction form with trig is actually a little bit easier to work with. And then if I really think about what this is saying is that the 8 is my pink number, because that's my opposite. And my hypotenuse is this diagonal, which I could put in blue. And so as I'm looking at this ratio, I don't know that these are the exact numbers that go there. I just know that it is the common ratio. So actually what I could look at is this reduced and get 4/5. So sine of 53 is approximately the angle used when I have a 4 opposite, 5. Well, what's the third side? We can use Pythagorean theorem. So a squared plus 4 squared equals 5 squared. Or hopefully by now you understand that this is a 3, 4, 5 right triangle. So the common, to answer the question, what common right triangle is probably used in the construction? It's a 3, 4, 5 right triangle. Let's finish this up just to make sure we are familiar with using Pythagorean theorem. 16 equals 25. Subtract 16 from both sides. A squared equals 9. A equals the square root of 9 plus or minus. We're going to reject the negative one. So A is equal to 3 as expected. Okay, so historically, we have a lot of connections to right triangles. So the actual angle between the base and the lateral faces of the pyramid are actually closer to 52 degrees. Considering the age of the pyramid, what would account for the differences between the angle measure in part A, which is 53 degrees, and the actual measure? And just to let you know, the Great Pyramids of Egypt are around 4,500 years old, or 4,500 years old. That's really, really old. So a few things may have happened. The block's extremely heavy. And the weight of those blocks on how they're able to actually transport them the great distances that they were and get them up to that levels that they were really implies some engineering and ingeniousness. But because they're extremely heavy, that could account for some settling or shifting. The other thing is, with this age, you may have had some erosion. You just never know. Okay, and then this speaks to the practical nature of the choice of a 3, 4, 5 right triangle. So why would they choose 3, 4, 5 right triangle? And if you're in construction, making sure that you have a 90-degree angle, this is a really good method, because we know that if I have a 3, 4, 5 Pythagorean triple that works, then that means that the triangle itself is a 90-degree angle. But to be truthful, 3, 4, 5, it's really quite easy to measure. So it's easy to measure compared to other ratios. And as a reminder, here are some of the other ratios: 5, 12, and 13, 8, 15, and 17. And even if you were working in inches, which wouldn't give you as great a distance as using feet, 7, 24, and 25 is another one. Measuring 13 feet might actually put you outside of the bedroom that you're measuring if you're using this in a construction. There's always the aesthetics. 3, 4, 5 happens to be the smallest integer Pythagorean triple. Okay, so this is just kind of showing you the practicality of some of the Pythagorean triples that you guys have worked with or seen. They can be used in construction, so now you have a practical application of them and so on. Okay, the other thing that we're going to do today is we're going to develop what they call the Pythagorean identity. And the first thing I'd like to point out to you is that this Pythagorean triple has a hypotenuse of 1, and that hypotenuse of 1 is really, really, really important. Okay, and as we've just seen, this is a 3, 4, 5 ratio. And so historically, how some of these numbers were developed is people started looking at more and more patterns. And so if I look at this 3, 4, 5 ratio, And I want the hypotenuse to equal 1. So if I have a 3, 4, 5 right triangle and I want the hypotenuse to be 1, all you have to do is divide each one of them. As long as I do it to each one, it's the scale factor. We must divide by 5. And so what you get is a 3/5, 4/5, 5/5 ratio, which comes out as, if I wanted to use a calculator, 6/10, 8/10, and 1. But let's just say we didn't have all that information. We only had what we have here. We can prove this with the Pythagorean theorem. So a squared plus 8/10 squared equals 1 squared. A squared equals or plus 6400ths equals 1. A squared equals 3600ths. If I take the square root of both sides, A is equal to 6/10. And so x is equal to 6/10. And we knew that at the beginning from our Pythagorean triple anyway. All right. And so that's kind of a nice thing. But something unique happens with a hypotenuse of 1. And so if we look at our sine, because we have the 53 degrees, we have sine of 53 degrees equals my opposite over my hypotenuse, which is really 8/10 over 1. And if I simplify that, now I have sine of 53 degrees is equal to 8/10. Or, in other words, this is equal to the sine of 53 degrees. Because of this idea of it being 1. And we can also look at the cosine of 53 degrees. That is approximately 6/10 over 1. And therefore, cosine of 53 degrees is equal to 6/10. And I can also replace this with cosine of 53 degrees. In other words, I can represent the sides of my triangles with trig functions. Represent sides of triangle with trig ratios. Okay? And so that really brings us to the next part. And then we see this triangle. Now, again, it's super important that the hypotenuse is 1 to build up this development. But as a general rule, with the hypotenuse equal to 1, we get this triangle. So the side opposite the angle, theta, is sine theta. The side adjacent to theta is cosine theta, as long as the hypotenuse is 1. I'm going to keep repeating how important that is. And so we can almost generalize using Pythagorean theorem. So all of a sudden we get this combination. So combining with the Pythagorean theorem, all of a sudden now we have sine squared theta plus cosine squared theta equaling 1 squared. And so what we come up with is an identity. Sort of a proof. Now you might be wondering, does it always work? Well, let's look. We've kind of done a little bit of work with our trig ratios, But you could also look at it in a general sense. Well, what happens if I just have the general statement of opposite, adjacent, and hypotenuse? So also proven for any side lengths. And this works with some of the stuff you've been working with in class, but I start out with, I have opposite squared plus adjacent squared equaling hypotenuse squared. If I wanted to create the one, I could divide each term by the hypotenuse squared. Which leaves me with opposite over hypotenuse quantity squared plus the adjacent. So you do have to understand your rules for exponents, but I'm allowed to pull that out. And this is just a 1. But opposite over hypotenuse is just sine of theta squared plus adjacent over hypotenuse is cosine of theta squared, which equals 1. In the final way, this is kind of just a notational thing, but we can write sine squared theta plus cosine squared theta equals 1. These things are actually equivalent. And now you have a secondary proof for the identity. And this does get used throughout. It's specifically addressed in pre-calculus and above, but you could see it on, say, the SBAC as they start quizzing you on your Pythagorean theorem knowledge and your trig knowledge. Okay, make sure you kind of look through these proofs, understand the important role of the hypotenuse of 1, how you can manipulate equations that you do know into new forms, and how those proofs come about. And then lastly, make sure you understand these vocabulary words of slant height, apex, pyramid height, and base, because they may come up in problems that you do in future classes, or again on various exams that you are going to take throughout the year. Thank you for your time.